Tamas, how are you?
I am well, thank you. How are you?
Excellent. I'm not too bad, thank you. Doing well. It seems to be going well so far. Tamas is a developer advocate at Cloudinary. Cloudinary is actually something we use at Snook as well. So we're big fans of everything you do at Cloudinary. And yeah, not going to give too much of an intro, Tamas, because I know it's we're up against the clock. So I'll hand straight over to you. And looking forward to the session.
All right, thank you very much, and also thank you for this opportunity. So while I'm sharing my screen here, is that visible? Can you see my screen? Yes, you can, I think. And is this still working? Hopefully it is. Okay, so as I said, thank you very much for this opportunity. And I'm here to talk to you about JavaScript and this thing called WebAssembly. So we're going to take a look at what you can do with the combination of these two languages. So I had a very quick introduction. So just to reintroduce myself really. So my name is Tamas. I work as a developer evangelist at a company called Cloudinary. I also run a training business, and I also happen to be a Google developer expert in web technology. You can also find me on Twitter. So you see the Twitter handle just below my picture here. I'm going to share the slides and some additional resources about my talk on Twitter. So please follow me if you would like to get access to that. Now, before we start, I thought to share a joke with you. Okay, so the question is, why do programmers leave their job? The answer to that question is because they don't get a raise. Now, it may be very early for some of you or too late for some of you, and you may not be getting this joke, but a raise and a raise. So that was the joke here. Anyway, so what we're going to talk about today is really, the web platform and how WebAssembly arrived to the scene and how it's changing the way we can create web applications. So this image that you see on my slide here is how the web platform used to look like in 2018 and before. So think about the web platform as having these two components. We have a virtual machine and we have the web APIs. So the web APIs would be the standard APIs that you'd be using from JavaScript, things like the fetch API, for example. And then you have the virtual machine inside the browser, which was able to execute your JavaScript code. And traditionally speaking, the web was aware of three languages. So you could run JavaScript. Browsers also understood HTML and CSS, and that was it. That was the web platform in 2018. And as we know, the web itself is progressing at an incredible pace. So there's lots of new framework, lots of new things that you can do on the web. And JavaScript, the language itself, is also progressing at an incredible pace. So there's lots of new ways to write JavaScript code. In the previous talk, we just heard about async and await and how promises were before that. So we had promises, async, await, and who knows what's going to be the next big thing for JavaScript. But it has certain limits, right? JavaScript is really just a scripting language for the web, and therefore it has a lot of limitations. As I said, because of the ecosystem is growing, we are getting a much better, or JavaScript is getting much better capabilities, but still there are lots of things that we can't do with JavaScript. For example, it's very difficult to achieve low-level tasks, right? So if you want to do some low-level processor-intensive task in JavaScript, it's going to be very difficult because JavaScript was a language that was created for something else. It's not for memory management and doing low-level tasks. And therefore, if you want to attempt that, because there are some things that you can do, but you're going to pay a performance cost because you're going to introduce some performance impacts, which you'd rather not do in a web-based environment. So what is the solution? Well, there's this thing called WebAssembly, which was created in 2015. And as you can see, I put an asterisk on the slide here because before WebAssembly in 2013, Mozilla created this thing called asm.js. And asm.js allowed people to run their application written in the C language as a web application. And this is predating WebAssembly because this was created before, and this allowed a very similar functionality to what WebAssembly can allow us to do today. And what's great, and if you've been following the news surrounding WebAssembly is the fact that, this is very recent actually. So last year in December, so at the end of the year, WebAssembly became a W3C recommendation, which means that now WebAssembly is something official. There's a spec, people can work on this, and it's all part of the official web ecosystem. So what is WebAssembly? Well, I have this description from Mozilla's website, which says WebAssembly is a low-level assembly-like language, a compact binary format that runs with near-native performance and provides languages such as C, C++, and Rust with a compilation target so that they can run on the web. So this is a very difficult explanation of what WebAssembly is, and I've come up with a much simpler one on my own, which I'm going to share with you, and it just says you can run native apps on the web. Okay, so this is the true power of WebAssembly. We can have applications or libraries of functionality written in a lower level language such as C or C++, and we can now execute that or use those functions and run them in a web context. Okay, so that's the essence of WebAssembly. So WebAssembly functions, or these functions that you create in C or C++, can be exposed to JavaScript. So what that means is you have a library that does, say, image manipulation using C. It's either something that you wrote or you want to leverage someone else's library and functions. You can select what functions are then going to be exposed to JavaScript, and in your web context, in your HTML page, inside a script element, using standard JavaScript, you can actually invoke that function, pass parameters to it, and do additional things. And I prepared a few demos, so we're going to take a look at these as well. Now, there's one thing that I've seen to pop up every now and then here and there on the internet, in various blog posts and other articles. And there are some people claiming that WebAssembly is going to replace JavaScript, right? So we have to forget about JavaScript, and WebAssembly is the next big thing. Now, that's not really true. Actually, it's actually slightly incorrect as well, because WebAssembly was not created to replace JavaScript or to eliminate JavaScript. WebAssembly is great for enhancing and for augmenting JavaScript. It basically gives extra powers to JavaScript, which the JavaScript language by design does not have. Okay, so WebAssembly is not here to replace JavaScript. So we had to look at how the web platform used to look like in 2018. How does it look today? So today we still have the web APIs, right? So there's a big list of web APIs, and we also have the virtual machine inside the browser that is capable of executing JavaScript code. But today, that virtual machine is also capable of executing WebAssembly code. Okay, so now, as of today, the web officially supports these 4 languages, or understands these 4 languages: HTML, CSS, JavaScript, and WebAssembly. Okay, so this is official. And of course, if we have WebAssembly, we must have something to work with the WebAssembly functions, and there is this thing called the WebAssembly JavaScript API. Okay, and it has a lot of methods, and all of these methods allow us to work with the WebAssembly code. And we can do things like loading a WebAssembly module. We can create new memory and table instances. And those are, so basically, a module represents a WebAssembly binary that has been compiled by the browser into executable machine code. Then we have the memory and table instances. So the memory is a resizable array buffer, and the table is a resized type of array of references. In other words, a table would contain functions, for example, from WebAssembly that we want to pass on to our JavaScript code and invoke it, for example. And then what we also have is this instance, which is just a module that is combined or paired with the state found in the memory and the table. And what's really interesting about this instance, we're talking about an instance of a WebAssembly script, essentially, is that it acts just like a JavaScript module would act. Okay, so it has kind of the same functionality as an ES 2015 module would have, meaning that it has exports and imports that work seamlessly under the hood. So the question is, how can you create WebAssembly, or how can you utilize WebAssembly code. And there's a bunch of ways that you can utilize here. So I'm going to share these 2 ways that I've actually used. So you either have the option to write some code in a very low-level language like C or C++, or as I say here on the slide, any other LLVM supported languages. So LLVM used to stand for low-level virtual machine, which I think they changed the name because what they referred to as a virtual machine 20, 25 years ago has now fundamentally changed. So you can think of LLVM as a compiler infrastructure or a set of compiler tool chains, right? So for example, Objective-C is another LLVM supported language, for example. So you have some code written in C or C++, and then you can use this tool called mscripton, which basically compiles your C or C++ code into WebAssembly. And if you produce a WebAssembly file, which will have a .wasm or a WASM extension. Once you have that file, you can load that file into the browser, and then you can consume it via JavaScript. Okay, so you can access the functions that you created in C and C++, essentially. Now, there's another way to create WebAssembly files. You don't necessarily need to use LLVM supported languages because there are some other languages that today compile to WebAssembly. So for example, .NET languages, Java, Ruby, or even Go have compilation targets. So you can write some code in Ruby or in Go, and you can compile it down to WebAssembly. And then the process is going to be the same because you load that WebAssembly binary into the browser and you can consume it via JavaScript. And the list of languages that you can use to create WASM files is really long, right? So there's a person who collected all these languages on GitHub, and here's a link. You can take a look at that. And this particular repository actually also tells you whether the language has full support for creating WebAssembly files, partial support, in progress, or plans to support WebAssembly. But the list is really long. So the good news is that if you used some backend language before, you can, or it's very likely that you can now create WebAssembly as well and play around with it and try it out. So as you can see, C#, Go, Java, PHP, Python, and also, and I learned this quite recently, TypeScript can compile to WebAssembly. So even if you're just a TypeScript developer, you can now create WebAssembly and play around with WebAssembly itself and see how it works. Okay, so let me give you a quick demo. I prepared 2 separate demos, and then I'm going to also show you a larger project that I worked on for a few weeks, actually. So let me change to my editor here real quick. And you will have access to the code repository here because I did share this on GitHub as well. So I have 2 examples, right? I have a very simple C file that is going to take a number and is going to square that number. Okay, so this is a very simple code written in C. I used this particular mscripton command to generate a JavaScript file called square.js. So square.js is going to be loading a file called square.wasm. So by running this piece of code here, I managed to generate a WebAssembly file and the JavaScript file as well so that I can invoke that WebAssembly file. Okay, and then what I did, I put that into an HTML page. I am using the WebAssembly JavaScript API to load the actual method from my C file, which is called inSquare. I specify the parameter that I need to pass in, or the type of parameter. So in this case, I'm going to pass in a number or an integer, and I'm also going to return an integer. And then I have right up here, I will have a very simple input button, a calculate button. And if I press the calculate button under the hood, what I'm going to be doing is invoking the WebAssembly int square function that I wrote in C. Now, this example is just showing you how to invoke something in C. I know this is not really meaningful because you can square numbers in JavaScript, but that's not the point of this demo. The point of this demo is to show you how to load, first of all, how to create something using mscripton, and then how to load that into the browser and then use that. So if I go to localhost 8080, I have this input box here. I put 2 and I get 4 back, which is squared. So if I put 4, then I get 16, which is 4 squared, right? So what happens here is from my HTML, I can invoke a method in a WebAssembly binary, and that WebAssembly binary was created from a C file, which is so here. So essentially, this is the function that gets invoked and executed by the browser. Okay, very simple example. The other example that I have is using Go. So I mentioned you can also use non-LLVM supported languages such as Go. So what happens here is instead of squaring a number, I now have a Go function called cube, which is going to return a number multiplied 3 times. Okay. The way Go is different from C and C++ and how you need to work with mscripten to generate the WebAssembly file is Go exposes this JavaScript global object. So from within Go context, you can actually access the document object inside your HTML page, and you can call things like get element by ID and then set the inner HTML of the particular element that you're capturing here. And then using this JS global, you can set the cube function that you created. So I'm basically exposing this cube function here to be a globally available object inside my HTML page, which means if I open the Go example, is that I can go ahead and fetch the WebAssembly file. And I didn't show that to you, but this was the command that I ran to create my WebAssembly file based on this Go file that I have here. And then I load in the WebAssembly file. Here's the module, here's the instance, the things that we talked about, so I get access to those. And notice that for the buttons on click handler, I pass in the cube method and I pass in the value of the input text as well, which is aligned before here, right? So I can actually access the cube method because it is being exposed by Go and the WebAssembly binary globally inside my HTML page. So if I now go to /indexgo, I again have the input box, and if I put 2 here, I now get 8. So I'm now using the cube function. Okay, so again, this is a very simple example because you can do mathematical operations inside JavaScript as well without a problem, but I'm just showing you that you can, access these functions that you created using Go or C. Okay, so let's take a look at a much more complex example. So let me put this away, and this is going to be a much larger project, as you can see, because I have more files here. But before we get to that, let me, I need to, I think, first go and shut down this server because we need a new one here. Okay, just using an HTTP server to serve up the contents of this folder. And refresh. Okay, image check. So what we're going to do here is going to be something very interesting because I mentioned that, I work for Cloudinary, and I've prepared a very quick demo of what Cloudinary can do for you so that you understand the demo that I created using WebAssembly and JavaScript. So what you have here is a standard, Cloudinary image that has been uploaded to Cloudinary. No changes to the image. This is an image which is a JPEG image, and the size of it is 583 kilobytes. Now, what Cloudinary allows us to do is to pass in various options to the URL. So I typed in fauto and qauto. So now Cloudinary is going to take a look at the browser and is going to say, okay, you are looking at this image using Google Chrome. Now, Google Chrome supports an image format called WebP, so Cloudinary will in fact render a WebP image and send it back to us. So if I take a look at the headers now, notice that the content type comes back as image WebP, and the file size is also just 32 kilobytes. So there's a massive optimization happening here behind the scenes. Okay, I can change the width and I can do all sorts of interesting things here. So what my project does here is that it's really nice that I can take a look at the returned image from Cloudinary and say, okay, that's a WebP image, or that's a PNG, or that's a JPEG. That's great. But I wanted to go a level deeper. I wanted to know if it's a PNG, does it support transparency? Does it have interlacing? If it's a WebP, which kind of WebP container do we use? And these are the type of questions that you can't really answer just by using JavaScript. You need something that is able to process the image at a much lower level. And this is, in fact, what I'm doing here. So I have various Go files. For example, if I open the PNG check, I access the image data buffer, and I can take a look at various pieces and bytes from the image data buffer. So for PNG files, I went through the PNG spec, and I read that bytes location number 24 tells you what kind of PNG you're looking at, whether it's grayscale, true color, index color, right? Whether it has interlacing or whether it uses the Adam 7 interlace or not. And all these pieces of information I could access using Go in a very easy way, right? So I can now use this to generate PNG info, and eventually using the JPEG, the PNG, and the WebP check Go files that I wrote, I get to basically take a look at the images that come back from Cloudinary and get these really neat and low-level details and just show that to users who are interested. So let's take a look at an example. And I also passed in the user agent because, as I said, Cloudinary is aware whether you look at the image from Chrome or Safari or Firefox, and it's going to generate the appropriate image. So I'm using fauto for this particular black car.jpg, which is just a car. I'm going to hit check using Chrome. And what we get back is a JPEG. Here's a size, and here's a quality, which is, did Cloudinary reduce the quality of the image or not? If I change this to width 500, for example, which is going to generate an image on the server side that has a width of 500, we're going to check, and now this time we get a WebP, and I can see, okay, this is a lossy WebP that does not have an alpha channel, and in fact, it uses a VP8 container. Now, I'm not going to get into the details of how WebP works, but there's a bunch of containers like VP8, VP8L, and VP8X, I think, that basically drive what kind of WebP you're talking about. And I can go ahead and, for example, change the user agent, which is only possible in Chrome by using the network conditions tab. So I'm going to say, okay, so I'm now pretending that I am Safari, right? So this also updates here, and I'm going to hit check. And now I'm getting a JPEG, which is again quality 88. But what if I now do say Q_auto, so remove the quality or reduce the quality of the image in a way that is not affecting the human eye? So let's go and do a check. And now I get quality 77 and the size went down. I could also, work with various PNG images. So let's try a PNG example. I think this is the right PNG example here. Okay, so that particular image, as you can see, there's a lot of information that I read about PNG. So it's PNG 32, there's a size, it has a bit depth of 8, its color type is true color with alpha, and it doesn't use interlacing. Okay, so there's a lot of things that you can now achieve and see because I have access to all the lower level interfaces via Go that I need to do further analysis of my images. And this is just scratching the surface, right? Because now you could do any sort of low-level processing, not just for images, for videos, for anything else. I've seen some examples where someone took an entire game, which was written in, I'm forgetting, maybe C++ or some other language, and now they are able to run it on the web. So I prepared a few resources for you. As I said, I'm going to share these slides. There's a sample repository. There's a bunch of case studies from Google, who, by the way, released that app called Scoosh.app, which also uses WebAssembly on the hood. They have a few very good articles that are related to memory management and lower level processing, and they do comparison between JavaScript and WebAssembly and how they perform in various browsers. It's a very interesting article for you to read if you're interested in this. And with that, thank you very much. And of course, we have a few minutes, I think, for Q&A. So if you have any questions, then
Absolutely,
please don't hesitate to ask away.
Absolutely, yeah. So please do ask your questions either on the sites or through Slack if you prefer. Yeah, a couple of questions come in. One about the usage of WebAssembly. Do you see it mostly as people who are trying to do something that is better suited in a different language, or is it because people have existing legacy code that they're trying to pull in, and as a result, rather than try and rewrite, they just ping it out with WebAssembly?
Sure, both. These are actually the two valid use cases that you just mentioned. So first of all, there are some things that you can't force, say, JavaScript into doing, right? So for example, JavaScript won't be able to read and parse WebP files, because for that you need there's a C library that has some WebP, what's it called, libwebp, I think that's the package. You can't use that in JavaScript. You need something that is compatible with that library to use that, right? So that's one use case. The other use case is, yes, if you have some code that you wrote in C or C++ that does something very specific, something very low level, it is now very easy to just port that into your web application and to use that. So these are two absolutely valid use cases. This is what people use WebAssembly for.
Cool. And another question about the performance hit. Obviously, my background is more Java based, so I see similar kind of like performance issues when people are trying to use JNI or something like that. What is the kind of performance hit that you see when dropping into a native language?
So that's exactly what that article that I just mentioned towards the end of the talk is about. So it's probably takes like a good 40 minutes to read, but basically what Google did was they created a WebAssembly binary using, I think there was a C or C++ example, that was a Rust example, and maybe another one, and then a JavaScript example, and then they run it past through various modern browsers, and then they measured all sorts of metrics. And it's very interesting to see that there was one particular browser where the JavaScript code execution took about 8 or 9 seconds, whereas the same code that they wrote in C or Rust took about literally 1.8 seconds, right? So it depends on what you're trying to do and how complex your code execution is going to be. But by default, because how WebAssembly is optimized for lower level languages, it has typed support for typed variables and other things. The code execution is by default in a virtual environment, in the virtual machine in the browser, is going to be a lot faster than say very complex JavaScript. But do read that article. So I'm going to, my screen is not shared anymore, but basically I'm going to share the slides, and do read that article by Google, which does go into the details of this.
Awesome. Thank you very, very much, Tamas. Really, really appreciate your support.
Thanks for having me.
And thank you for the great session as well.
All right. Cheers. Enjoy the rest of the sessions.
Will do. Thank you. Bye.